Okay, so the next thing that we have here, basically in the previous video we talked about the fundamental theorem of arithmetic, and for example one of the basically one way, just one way that you can use this theorem is that, for example, let's say that you have some number, for example 4 raised to the power n. You want to know, for example, you have some number 4 raised to the power n, where n is a natural number, basically where n is a natural number. Okay, so then now you want to know basically whether there is any value of n, for example, for which 4 raised to the power n ends with a 0, okay? So that means that basically the unit place in that number becomes 0. For example, let's say if n is equal to 1, then 4 raised to the power 1 is equal to 4. If n is equal to 2, then 4 raised to the power 2 is equal to 16. If n is equal to 3, 4 raised to the power 3 is equal to 64, and so on and so forth. Okay, so now you have all of these numbers, and you have all the natural numbers, and then you can raise 4 to all of those numbers, and you want to know if there is any value of n for which 4 raised to the power n it can actually end with a 0. Okay, so now one way that you can use this fundamental theorem of arithmetic is that to solve actually this problem, if 4 raised to the power n were to end with a 0, basically then it would have to be divisible by 5. Okay, so basically if 4 raised to the power n were to end with a 0, then it would have to be divisible by 5. That's basically the divisibility condition or test for 5. Now if any number is divisible by 5, then it will have at least one factor of 5 in its prime factorization. Okay, so now you can use the prime factorization of 4 raised to the power n. Now the prime factorization of 4 raised to the power n is basically 4 raised to the power n, which is equal to the factors of 4 are you can write it as 2 raised to the power n times 2 raised to the power n, which is equal to 4 raised to the power n, and or you can write it as 2 raised to the power 2 whole raised to the power n, and then that's equal to 2 raised to the power 2n. That's raised to 2 raised to the power 2n. So what this means is that 4 raised to the power n, which is equal to 2 raised to the power 2n, the only prime factor that this number has is a 2. Okay, so there is no 5. There is no 5 as a prime factor that exists in this number. So that means that this number is not divisible by 5. That means that this number, for no value of n, can end in a 0. So that's basically, for example, one way that you can and of course we are using the fundamental theorem of arithmetic. And here basically the uniqueness of the fundamental theorem of arithmetic guarantees that there are no other primes in the factorization of 4 raised to the power n other than 2. So that's basically how you can, for example, use, so you can see how, you could actually use this theorem in many different ways depending on the situation you are in. So now let's go to basically let's go back to where we were. I don't really know where I was. I think we were so basically we went through the fundamental theorem of arithmetic, and we wanted to prove that, we wanted to find a way to prove that numbers like square root of 2, square root of 3, square root of 5, and so on and so forth, are that these were basically irrational numbers. But before we can do that, we need to basically do a couple of things. First, we need a theorem. Now, the theorem that we have, of course, we have used this theorem before, but now we want to first basically prove it, and then we will use it for square root of 2. Okay, so now we have a theorem here, and I guess I will have to somehow enumerate these theorems in order that we can actually use these theorems over and over again, and then I will write these theorems somewhere and somehow categorize them into different categories so that we can use them. But for now, I'm just going to give this theorem some number. For example, since this theorem, for example, is related to numbers, I am going to call it, for example, n1. Start from here, start from number 1, and then and then we will, whatever theorem basically we get related to numbers, we will put them in the category numbers, n1, n2, n3, and so forth, so that we can use them over and over again. Otherwise, in different chapters, the theorem numbers change, so then we don't, we will have a problem there. Okay, so now there is a theorem, I'll call it theorem N1, okay? So theorem N1, N standing for numbers, and 1 for basically number 1. So let P be a prime number. Okay? If P divides A squared, if P divides A squared, then P divides A, then P divides A where A is a positive integer. Okay, so basically, so what that means is that if P is a prime number, okay, when we say if P divides A squared, what that means is that basically A squared is divisible by P. For example, let's say that, let's take A as 3, for example. If A is equal to 3, then A squared is equal to 9. Okay, so now let's say that let's take this as something else. For example, let's take this as 9. So let A be equal to 9, and then A squared will be equal to 81, and 81 is divisible by 3. Now let P be equal to 3, for example. So now when I say basically if P divides A squared, what that means is that A squared is actually divisible by 3. So what that means is that A squared, if you divide it by P, which is equal to 81 divided by 3, I'm going to get a 27. So it's divisible. So now if P divides A squared, meaning that if A squared is divisible by P, then P divides A. Then basically P divides A, meaning that A is divisible by P, meaning that then A, which is equal to 9, is also divisible by P, which is equal to 3. That's equal to 3. And that's basically something simple that you will realize on your own as well. If you work with numbers for a little bit and do some calculations, you will realize this on your own. I kind of realized this while I was doing some calculation. I was basically solving some problems, and then I noticed the same thing, that basically if you have a number, and if that number is divisible by some number, then the square root of that number is also divisible by that number as well. But then, of course, I didn't think that it was that important. I didn't think it was that important to make a theorem out of it, but it seems that it is. So that is that basically. Now, the way that you can actually prove this is using the fundamental theorem of arithmetic, the fundamental theorem of arithmetic. And so here we say that basically P let p be a prime number, and if p divides a squared, then p divides a as well, where a is a positive integer. So now the prime factorization of a, so here basically a is basically this number over here. So now if you start with the prime factorization, of a would be a is equal to p1, for example, p2 all the way up to p of n, where p1, p2 all the way up to p of n are primes, and not necessarily distinct. Meaning that there could be repetitive factors in there, okay, which makes sense, right? And so if the prime factorization of a is basically p1, p2 all the way up to p of n, therefore a squared is going to be equal to p1, p2 all the way up to p of n, basically the prime factorization of p times the prime factorization of p, because a squared is equal to a times a. So this is a, and this is also a. So p1, p2 all the way up to p of n. And that is equal to p of 1 squared times p of 2 squared times all the way up to p of n squared. And that's basically, so this is the prime factorization of a, this is the prime factorization of b. Now we said that over here, we said that p divides a squared. We said that p divides a squared, right? So then based on the, I don't want to write everything down. So then based on the fundamental theorem of arithmetic, it follows that p is one of the factors of a squared, is one of the prime factors of a squared. And using basically the uniqueness part of the fundamental theorem of arithmetic, then we basically realized that the only prime factors of a squared are basically p1, p2 all the way up to p of n. And that's supposed to be the unique factors of a squared. So then basically, p is going to be equal to, so now let me actually write this down. So we said that p divides a squared. Therefore, from the fundamental theorem of arithmetic, from the fundamental theorem of arithmetic, okay, and the fundamental theorem of arithmetic, it follows that p is one of the prime factors of a squared. It follows that p is one of the one of the prime factors of a squared. However, using the uniqueness part of the fundamental theorem of arithmetic, using the uniqueness of the fundamental theorem of arithmetic, we realize that the only prime factors of a squared, the only factors of a squared are P1, P2 all the way up to P of n. Now you need to make sense of this sentence over here. So basically here we said that the factors, the prime factorization of a squared is basically P1 squared times P2 squared all the way up to P of n squared. And of course over here we said that the prime factorization of a was P1 times P2 all the way up to P of n, where P1, P2 all the way up to P of n are primes, not necessarily distinct. Okay, of course that makes sense, because when you factorize a number, you could get, for example, 2 2s, 5 3s, 3 8s, and so on and so forth. So not necessarily distinct. Now, therefore, so then if that's the prime factorization of a, then a squared is going to be this thing over here, whatever you've written over here, times itself, because a squared is the same thing as a times a. So now here we said that p divides a squared, meaning that a squared is divisible by p. So that means that p has to be one of the factors of a squared. Therefore, from the fundamental theorem of arithmetic, it follows that p is one of the prime factors of a squared. Makes sense, right? But now, using the uniqueness of the fundamental theorem of arithmetic, we realize that the only factors of a squared are basically P1, P2, and P of n. It means that it doesn't matter. They're basically the unique factors are raised to the second power, the third power, the fourth power. It doesn't matter. The only factors of a squared would be basically P1, P2 all the way up to P of n. What that means is that, for example, if you have some number like, I don't know, let's say you have, let's make up a number. So let's say you have 2 times 3 times 3 times 4 times 4 times 4 times 5 times 6, for example. So this is 2 times, this number is 2 times 9 times 64 times 30, and that's equal to 18 times 64 times 30, and that's equal to 54. 0 times 64, and 54 times 0 times 64 is equal to, let's forget about this 0. So 16 1, 21, 24 2, 32, and then you have 6 5 4 3, and then that's equal to 3 4 5 6 0. Okay, so now if you have this number over here, let me actually multiply these numbers. So 2 times 3 times 3 times 4 times 4 times 4 times 5 times 6 equal to 34,560. Okay, so now this number over here is actually equal to 34,560. It's actually equal to 34,560. Okay, now 34,560, when you prime factorize it, of course you're going to get these numbers over here, and it's the same situation that you have over here, that you have, for example, p1 squared, p2 squared, p of n squared, p of all the way up to p of n squared. And if I rewrite this thing over here, I write 34,560 is equal to 2 times 3 squared times 4 cubed times 5 times 6. Okay, so now the prime factorization of this number, is actually this thing that you see over here. But the only prime factors of this number are, it doesn't matter to what power they have been raised to what power they have been raised. The only unique factors of this number 34,560 are 2, 3, 4, 5, and 6, meaning that you can say that this number is divisible by 2, divisible by 3, divisible by 4, divisible by 5, and also divisible by 6. So that's basically the meaning of that sentence there. So now let's see what we have here. So the only factors of a squared are p1, p2, all the way up to p of n. So since basically since p divides a squared, now since p divides a squared, therefore p is one of the prime factors p1, p2, all the way up to p of n. Okay, now since actually a was equal to p1, p2, all the way up to p of n, and then we said that p is one of the prime factors p1, p2, all the way up to p of n, and of course p's basically prime factorization is the same thing. Therefore you can say that a is divisible by p, or p divides a as well. P divides a as well. Okay, so that's basically that. So I call this theorem, I call it basically I don't know, N1 as I called it over there, and I'll simply make a list of all of the theorems that we happen to work with here, and then I'll publish them somewhere on the internet, and then whenever I want to refer to something, I just refer to the number of the theorem we have talked about, and then you can get a copy of all of those theorems from the same place, and then you can basically that way we can make sure that we are basically both on the same page. Okay, so now let me get a couple of things done. I'll be back with the rest of this thing. Okay, so now in order to basically we all basically kind of know that basically square root of 2, for example, is irrational. But in order to understand why that's irrational, you can actually try to prove that it's irrational. And it's actually interesting how you can prove that. And you can prove that using you can prove that using the same technique. Why is it so? Okay. We have some space here. Okay, so you can prove that using the same technique that we talked about when we were talking about proofs in mathematics, which was called proof by contradiction. Proof by contradiction. And if you remember what we said about this way of proving things, I think I didn't give you, I did give you one example there, but we will use it over here in order to prove that, prove square root of 2 is irrational. Okay, so so now if you want to use proof by contradiction, in order to do the same thing, usually what you do not usually, almost all the time as far as I know, is that you have to basically assume something, assume the negation of this statement. If the statement is square root of 2 is irrational, the negation of this statement would be square root of 2 is not irrational, or square root of 2 is rational. So then you have to basically assume to the contrary, that that square root of 2 is rational. Okay, so and before we go through the steps are usually done in such a way the steps are usually picked in such, or chosen in such a way, that you can create some sort of contradiction that somehow contradicts your now let's go through the steps, and then I will talk about that more. So let's assume to the contrary that square root of 2 is actually rational. Okay, so then basically, based on the definition of rational numbers, if a number is rational, then you can find two integers, for example a and b, such that basically a and b are integers, and b is not equal to 0, and then that number can be expressed as a ratio of a and b, something like this. So we can find integers we can find integers, for example, r and s, and basically s not equal to 0, such that the ratio of these two integers, meaning r to s, and s not equal to 0, and that way you know that s is your denominator. Otherwise you would have taken r not equal to 0, right? So such that r divided by s is equal to square root of 2. If square root of 2 is a rational number, then you can actually express it as a ratio of two integers, and the denominator, as you know, is not supposed to be equal to 0. So far we have no problems. Now we can safely assume or suppose that r and s have a common factor. So then we can divide by the common factor both the numerator and the denominator, to get a and b, for example. So and what that means is that a and b are now co-prime. The co-prime basically co-primes, meaning that they have no common factors other than 1. A and b being co-prime. So what this step means is that, for example, let's say that the two numbers have, for example, I don't know, for example, 8 and 2, right? And 8 and 2, if you have 8 divided by 2 as a rational number, these two numbers, the numerator and denominator, have a common factor, which is 2. So 8 can be written as 4 times 2, and you have a 2 in the denominator. So you can divide by the common factor to get 4 and 1. So 8 divided by 2 is the same thing as 4 to 1, right? So the same thing happens over here. Now these two integers are not co-prime because they have a common factor other than 1, and the common factor was 2. Now, but these two integers are co-prime because the only common factor that they have is actually 1, meaning that 4 is nothing but 4 times 1, and 1 is nothing but 1 times 1. And the only common factor that they have is 1. In simple language, what that means is that you cannot simplify this fraction any further. If you cannot simplify a fraction any further, what that means is that the numerator, the number that you find in the numerator, and the number in the denominator are then called co-prime integers. It's just a fancy word for simple concept. Okay, so then so now we have a and b, and a and b are now co-prime. So then we can write a divided by b is equal to square root of 2. And And so what that means is that a is equal to b square root of 2 if you basically cross multiply. And if you square on both sides of this equation, you'll get a squared is equal to 2b squared. 2b squared. And a squared is equal to 2b squared. Therefore 2 is a factor of a squared, or a squared is divisible by 2. So therefore a squared is divisible by 2, because as you can see, a squared has basically 2 factors here as far as we know. Basically it's one of them is b squared, meaning that a squared has been written as a product of 2 and some other number, so it's divisible by 2, right? So now if a squared is divisible by 2, we said that so by the theorem that we just did, it was theorem n1. What that means is that, so now by theorem n1, a is also divisible by 2, right? So we can say a, since a is divisible by 2, so I can write a as 2c, for example, for some integer c. Okay, for some integer c. Now here we said that a squared was equal to 2b squared. Here we said that we had basically a squared is equal to 2b squared. Now since a is equal to 2c, you can substitute a here. So basically 2c whole squared is equal to 2b squared, and 4c squared is equal to 2b squared, and then that means that 2c squared is equal to b squared. That means that b squared is equal to 2c squared. And what that means is that so now b squared is divisible by 2, because as you can see here, one of the factors of b squared is 2 over here. And so, and by theorem n1, b is also divisible by 2. So what we said is that, so basically, so now a is divisible by 2, divisible by 2, and so is b. But we said that but basically that contradicts actually, contradicts the fact that a and b are coprime, meaning that if two numbers are coprime, they're actually not supposed to have any common factors other than 1, but now we have found that they have a common factor, at least one common factor other than 1, and that is 2. So this is a contradiction, right? And contradiction is not supposed to be there. That means that there is something wrong. Okay. Now this contradiction has arisen because of our incorrect assumption that square root of 2 is rational. Otherwise this contradiction would not have arisen. So basically, we conclude that square root of 2 is irrational. So basically what you can see over here, you wanted to prove that square root of 2 is irrational, right? And you wanted to do that by proof by contradiction. So what you do is that you assume to the contrary that the square root of 2 is not rational, is actually not irrational, or basically rational. And then you have to basically take the kind of steps where you get to some sort of contradiction, something basically you have to basically to basically somehow take the kind of steps in such a way that some fact or some fact is contradicted in the process. And since in the process some fact was contradicted, that means that your assumption was wrong. And since your assumption was wrong, that means that the negation of your assumption was right or true. And then that actually simply proves what you wanted to prove. That's basically how this thing works. Or we could do also one more example here. That, for example, how a square root of 3 is irrational, and so on and so forth. But I need to take a few minutes off and then decide whether I want to do square root of 3 as well. So let me take a few minutes off. Okay, so now using the same logic, you can actually prove that square root of 3 is also an irrational number. Okay, so we don't have to really go through that example. It takes some time, and it's basically the same thing. So so now the next thing that we can do, basically previously, well, of course I haven't talked about this previously here, but you know that the sum or difference of a rational and an irrational number is irrational. There are bases basically about something about the sum or difference. So the sum or difference of a rational and an irrational number is basically irrational. Okay, and also the product and quotient of a non-zero rational and irrational number is irrational. So the product and quotient basically means division of a non-zero rational and irrational number, of a non-zero rational and irrational number is also irrational. Okay, so now we are not going to prove basically these, the general case for each of these statements here, but we can prove, for example, some particular cases of these general cases. So for example, let's say that you want to show that, I don't know if I have enough space over here. I don't really. So I can't do this here. I'm going to let's close this, and then I'm going to basically create another one of these. Resize and make this, for example, 4,000 pixels times 6,000 pixels, for example. And okay, so a new layer here, and there you go. Okay, so for example, you want to show that we said that the sum or difference of a rational and irrational number is basically an irrational number, meaning that you have the sum. Let's say that you have a rational number, rational plus or minus irrational, is going to be equal to an irrational. Okay, so for example, if you want to show that 5 minus square root of 3 is irrational. So how do you do that? So you can use basically proof by contradiction to show this result. Okay, now in order to use proof by contradiction, let us assume that 5 minus square root of 3 is rational. Okay, so if this is a rational number, so then we can find two integers, let's say r and s not equal to 0, such that 5 minus the square root of 3 is equal to is equal to the quotient of these two integers, r divided by s, r divided by s. Okay, now so what this means is that if you actually cross multiply here, you'll get s times 5 minus square root of 3 is equal to r, right? Or you can actually do something else. You can, let's see how I can get to some sort of contradiction. If 5 minus square root of 3 is equal to r by s, then, okay, so then what you can do, let's say that this is equal to r to s. So now let's assume that, or let's basically suppose that, for example, suppose that r and s have a common factor. Now, if you divide both by the common factor, okay, what you will get is divide both by the common factor to get a and b, for example, a and b being co-prime. I think now you can understand all of the logic that I have written here. It's not that complicated. I mean, it's not complicated at all. The same things I have done in the previous example as well. So now now we know that a and b are co-prime, right? So what that means is that now, so we can say 5 minus the square root of 3 is equal to a divided by b. Now, if you cross multiply here, you'll get 5 minus the square root of 3 times b is equal to a. Okay, so that means that basically, first of all, you know that now 5 minus square root of 3 is a factor of a. Okay, is a factor of a. Now I think if we square here, okay, so they have actually used an interesting logic here. You see what they have done? Is that well, if in order to I mean, before you start, of course, before you start with writing the solution or trying to prove, before starting with writing your proof, you have to have some sort of strategy, otherwise it's not going to work out for you. And I did the same. I actually, when I started, I had no strategy really, which makes actually no sense. Okay, which really makes no sense. So so now we want to prove that basically 5 minus square root of 3 is irrational, right? So so now what we have done, we said that we want to use basically proof by contradiction. So then we assume that 5 minus square root of 3 is actually rational, right? Is actually rational. So is actually rational. Now what you can do, now what they have done the same steps over here, as I can see in the text here. But then they have shown that square root of 3 is a rational number, meaning that if in this equation, if you basically solve for square root of 3, what you will get is that take square root of 3 to the other side of the equation, take a by b to this side of the equation, what you will get is 5 minus a by b is equal to basically positive square root of 3. So take square root of 3 to the other side of the equation, a by b to this side of the equation, so this becomes 5 minus a by b is equal to square root of 3. Now what this means is that if you add these together, if you add these two together, you'll get b, and that's 5b minus a. So then this is equal to square root of 3. And as you can see over here, basically b and a, we said that a and b belong to the set of integers. They were two integers, and b was not equal to 0. So now if you have 5b minus a, that's going to be some integer, and then you divide it by b. So this is actually some fraction, like for example, I don't know, c divided by d, where d is not equal to 0. That means that if this is equal to e, then you can call e a rational number. Okay, so what that means is that now you can say that square root of 3 is actually a rational number. Okay, so now you can say that square root of 3 is rational. But we proved that square root of 3 is irrational. Okay, and that is a contradiction. That is a contradiction. And this contradiction arose because of of the incorrect assumption that 5 minus square root of 3, here we assume that 5 minus the square root of 3 is rational. So that means that our assumption was actually wrong. So we conclude that 5 minus square root of 3 is irrational. And that's basically what we wanted to prove. We wanted to show that 5 minus square root of 3 is irrational. There is one more example here, which is also interesting. We will do that as well, and then we will end this video. And I think we are at the end of this part. We basically mainly wanted to talk about irrational numbers, and we have actually reached our goal, except for this last example. We'll do that as well, and then we're done with this part. Now, basically we also said that basically the product or quotient of a rational number and irrational number, meaning that if you have, for example, a times b or a divided by b, if for example, let's say that a is a rational number, a is a rational number, b is an irrational number, okay, and basically a and b not equal to 0. If they're not equal to 0, then the product and the quotient of these two numbers is going to be either this or this one is going to be an irrational number. Okay, so for example, let's say that you want to show that 3 square root of 2 is irrational. Okay, so again we can use proof by contradiction. So I assume to the contrary that 3 square root of 2 is rational. Okay, and if it's rational, then we can find co-prime integers a and b b not equal to 0, such that a divided by b is equal to 3 square root of 2. Now a divided by b is equal to the 3 square root of 2. Now 3 square root of 2, if you here basically solve for square root of 2, square root of 2 here is equal to a divided by b divided by 3, which is equal to a divided by 3b. And this is a rational number because this is an integer, so this is going to be some integer divided by some other integer. So that means that square root of 2 is rational. which basically which contradicts the fact that square root of 2 is irrational. We already know that square root of 2 is irrational. We have not proved it, but we know it. I mean, of course, we know that, I mean, it was actually over here to be proved, but of course I just chose not to do it. But we are basically assuming here that we have already proved that square root of 2 is irrational, so we can actually use it in our logic. That's what I mean. So basically, this contradiction arose, because because of our wrong assumption, or our incorrect assumption, that square root of 3 square root of 2 was a rational number. So we conclude that 3 square root of 2 is irrational. Okay, so that is that. So basically that is all that we have here. I mean, I think I have, I mean, at least for now, we have talked enough about irrational numbers. The next thing that we have here is basically a couple of things about rational numbers and their decimal expansion, their decimal representation, and I think that's it for at least for now. So I'll see you in the next video with rational numbers. Thank you.